Okay, some of you will notice that I'm not Cameron Moye. Cameron's my grad student. He is under the weather today, and so talk will be given by me. See, do we have the advance here?
Big green button?
Yes, big green button. There you go. So I'm trying to absorb all the words from the last presentation. Oh my gosh, we've got things to be concerned about. And I'm glad I'm not the first speaker who's going to be talking about future samples as opposed to samples that we have in hand. So Cameron and I have been looking at how to get at areas for sampling volatiles that doesn't involve going into a PSR. A lot of work has been done on characterizing volatiles that potentially are at the surface at PSRs, but we're interested in what is below the surface that we could potentially sample outside of a PSR with something like a drive tube or a double drive tube. So looking at the Artemis 3 candidate landing regions, and we'll just take an example here. So we're focusing on South Pole illumination conditions that might either give us opportunities for sampling regolith that either has ice or has alteration from ice that may be in a transient state from time to time. So even though the PSRs might be the most likely place to find them, the lack of sunlight definitely keeps those surfaces very, very cold. So, but there are some issues for accessibility for astronauts, not the least of which is sometimes slopes associated with getting into craters where there are PSRs, even small PSRs. But regolith is an excellent insulator, so volatiles are likely to be stable outside of PSRs in the upper meter or perhaps deeper. And here's a nice image of Gene Cernan collecting a double drive tube at Apollo 17. You'll see that slide again, that picture again in a subsequent presentation. So where are the areas we can sample with volatiles, where we can sample volatiles, and we're going to focus on illumination conditions. So what we also want to do is make sure that astronauts can access these areas. So we're looking at areas with low slopes, slopes less than 20 degrees that can be walked to, and slopes within a 2-kilometer radius of a potential landing site. And what Cameron is doing is integrating slope, thermal, and illumination conditions to gain a predictive capability that we can quickly employ given a particular landing site to determine, to predict the access to volatiles that are in the upper meter. Okay, so here are the methods. Cameron makes use of QuickMap, the expression layer feature in Lunar QuickMap, and this allows him to highlight regions that meet both the thermal and accessibility criteria for potential subsurface volatile retention. So this is basically using a number of layers to get at sort of a relational database of favorable areas. So slopes less than 20 degrees. We picked an average summer surface temperature of less than 125 degrees, and so we're using diviner data for this, 125 Kelvin, I should say. And then looking at the fraction of the 18.6-year lunar cycle that areas are exposed to sunlight. And so you see in the lower right here, the scale going from 0%, that's a PSR. Well, you can see it's in the light blue. And then in darker blue, 0 to 10% solar illumination, all the way up to 50 to 60% in the purple. And the data sets that we're using is shown there: slope, LOLA, temperature from diviner, polar summer average temperature, and then solar illumination at 60 meters and 120 meters LOLA-derived solar illumination. Okay, so here's an example, Faustini Rim A. We'll just show this, two possible landing sites that one might pick, assuming that HLS can really stick it. So areas A and areas B, and on the right-hand side, you see Cameron's color-coded scheme where the temperatures are below 125 Kelvin, and the colors represent the different degrees of solar illumination. And so you can clearly see the PSRs, the light blue areas that are typically in craters. And then around them, areas that have 0 to 10, 10 to 20, 20 to 30, et cetera, percent illumination. And that's what we're going to focus in on. Okay, so just looking at those two areas in some detail, you see that there's quite a difference in the accessibility to areas. And here we're focusing particularly on those that have 0 to 10, 10 to 20, and 20 to 30% average illumination, because those are the areas that correspond best with where we think subsurface ice can be stable. Okay, and so we'll keep this quick and look at conclusions. So this allows us to have a sort of a first step in assessing astronaut accessibility to subsurface areas where we think water ice could be stable, or there could be alteration from transient heating in sublimation or loss of water. Can be quickly deployed to assess an initial potential for sampling volatiles at a given site, and can help narrow down which sites warrant further modeling at higher resolution. Now, one thing we're doing here is using the illumination conditions that are at a very high resolution, and that allows us correlating that with other data sets that give us an indication of temperature and accessibility to water ice in the upper meter. So next steps here will be to evaluate illumination conditions during specific mission timeframes. And you may not know this, but many of you probably do. With QuickMap, you can run some of the more sophisticated routines that allow you to model the illumination conditions at a given future time. So you want to look and see what's the illumination like in September of 2026. You can do that. And we can use that kind of modeling to say what really is going to be accessible given illumination conditions during a specific time. And then develop a sort of a more quantitative method for determining the volatile bearing potential. So this is ongoing work, and Cameron is probably listening, and if you have questions, I'll defer to him. Thank you.
Do you have any questions coming up to the microphone online? Type them in. We have actually time for this. So. Let's see, one coming up. Anything else you would like to add?
There is one thing. I don't know if the slides can be brought back up. I actually missed his last slide, which is an acknowledgement, but I can state the acknowledgements. Yes, here we go, very good. The Artemis 3 geology team, of which Cameron and I both participate, and the LROC science team, notice I have my LROC hat on, and LROC is largely responsible for what we have in Lunar QuickMap. And that's, hats off to Mark Robinson for having the foresight to know how important Lunar QuickMap would be, and I'm sure everybody in this room uses Lunar QuickMap at one time or another. So NASA, ASU, and ACT, which does QuickMap. Thanks.